Welcome to this presentation on NovaSAR and SSTL S1 to 4, SAR and EO data fusion. I'm Rebecca Couchman-Crook, the lead author on this piece from a team at the Defence Science and Technology Laboratory in the UK. A quick note, I'll be referring to SSTL S1 to 4 as just S1 in this presentation to make it easier. So a brief introduction to the satellites. They are both in a circular sun-synchronous orbit at an inclination of 97.8 degrees and at a 580 kilometre altitude. They don't have a repeating ground track, which obviously limits some of the uses of the data. NovaSAR is a synthetic aperture radar satellite and can image in all four polarizations. On board, it also has an automatic identification system receiver, which allows information from ships to be gathered. S1 is an electro-optical satellite that has a multispectral sensor and a panchromatic one. What is most unusual about the two satellites is that they are only 15 minutes apart on the same orbit, so this provides an interesting basis for uses of the data. This is just a visual of the satellites in orbit, so you can get an idea of their coverage compared to each other, showing their access tracks. Some of the example use cases of this sort of satellite configuration could be camouflage detection, bathymetry, vessel detection including dark vessels, and these are ones not transmitting AIS data, ship weight detection, building image sets for machine learning, looking at airport and landing strip availability and condition, topographic corrections using information from both sensors, shadow removal using information from both sensors, target movement, oil spill detection, improved scene interpretation, and vegetation classification. As the focus of this presentation, I want to highlight some of the demonstrated use cases of the data from the work of our team. As a general starting point for utilising the images, we made use of the ESA Toolbox Snap 7.0, which has a specific NovaSAR plugin. Firstly, the challenge of identifying dark vessels in imagery. Again, to clarify, a dark vessel is one that is not broadcasting AIS data, so its identity and location are unknown. The combination of the SAR and AIS data makes the identification of these targets much easier. The image on this slide shows the SAR image in characteristic black and white, and the AIS data is overlaid as slightly offset yellow dots, showing the location on the image. The dark vessel is in a red box to the left of the screen, as it has no accompanying AIS dot, and if it were present, it would be to the right of the red box. There are challenges when making use of AIS data in congested waterways, as there is a chance that not all signals will be picked up by the receiver, making intentional non-broadcasting harder to determine. By further combining the information in AIS transmissions, such as boat type, the SAR pictorial information and perhaps water depth information can be combined to identify illicit activity. For example, a tanker would not be in water less than 1 metre. On the theme of vessel detection, two automated ship detection methods were trialled using NovaSAR imagery. These were the constant false alarm rate, or CFAR, and the convolutional neural network, or CNN. When compared, the CNN method outperformed the CFAR method when there was no native training data. Additionally, it was verified that non-native training data could be used to detect ships in S-band data. The finding of a CNN method of detection works best with no native training data suggests that this technology could provide an integrated ship detection capability from the start of operations in something akin to the NovaSAR platform, avoiding the need of amassing training sets first. Additional details as to this work may be found in Carmen T and Kolhatka A 2020, a comparison of CFAR and CNN vessel detection methods for S-band NovaSAR images. By using the different bands on the multispectral images from S1, we are able to create a variety of vegetation indices. Health of the vegetation and classifying vegetation coverage and ground type can all be assessed with different combinations. By comparing these vegetation indices, we can make sense of puzzling features that are shown by SAR images. This is highlighted well in the Everglades image on the left, that has mysterious rectangular features with different reflectivity, and using the vegetation indices we can tell that this is because of different levels of vegetation cover on areas cleared for farming. Further to this, Indication as to the ground cover and the vegetation that is at a location can be gained from the band combination of the image on the right. This band variation shows non-vegetated land appears in magenta, commonly buildings and sand, and dark blue, commonly water. Vegetation coverage can be classified with greener areas being closed canopy, acid yellow being open canopy or shrubs, and golden yellow showing areas of grass. One use case that could make use of the SAR imagery specifically was oil spill detection. Oil spills appear as dark areas on SAR images. In the images on this slide, anomalous pixels are outlined in blue boxes and the oil spill is outlined in red boxes. Two methods of detection were trialled. Firstly, a grey level co-occurrence matrix method. This utilised a textual analysis of the image to detect the contrast of the oil spill when compared to the surrounding image. On this contrast image seen here centred top, a k-means unsupervised classification was performed, and by determining the cluster that showed the oil spill and colouring this green, the oil spill could be picked out clearly. The benefit of this method was that the full extent of the oil spill was much more visible than the other method used. This second method was the SNAP inbuilt oil spill detection feature, which uses thresholding to identify likely pixels, and then clusters these based on the area covered by neighbouring pixels. This led to a reduction in anomalous pixels, but the full extent of the oil spill was not defined. Movement of a target can be identified at a basic level between images by utilising ones taken by each sensor in the same orbit 15 minutes apart. This is shown by the image here where a boat moves into the white box in the latter acquisition. Additionally, this can be combined with AIS data to give greater assurance of moving targets' intentions. Both EO and SAR data can be used for estimating water depth. This study trialled retrieval methods for both. The advantage of having the images taken 15 minutes apart means that they can be considered contemporaneous, as the processes that govern the water depth are unlikely to change within this time frame. This allowed a direct comparison of the depths obtained. It was found that the EO images gave better information but only in shallower depths of less than 20 metres. The SAR can be used from around 50 metres up to 100 metres. The overlap in the coverage means that results can be combined to help reduce errors in retrievals in both datasets. They can also provide alternative sources of bathymetric data, as SAR performs best in cloudy conditions, whereas EO is better in rougher sea states. In summary, this work has demonstrated a variety of use cases for near-contemporaneous data and also for combining SAR, AIS and EO data. This combination of sensors in one platform or linked platforms would be a useful capability. And finally, onboard algorithms should be a focus for future mission concepts, bringing many added benefits. Thank you for listening, and I'm happy to answer any questions you have via email. Thank you.